So let F be a field. We consider algebras over a field F. Well, they could be infinite dimensional, but I still want them to be finitely generated. So the generating subspace V is finitely generated. Well, now some problems related to infinite dimensional algebras. This is a kind of the grand dame of the ring theory, the Courage problem. An element A is said to be algebraic if there exists a polynomial such that that element is a root of the polynomial, like every matrix is a root of its Hamilton-Kelly polynomial. And an algebra is algebraic if every element is algebraic. In particular, an algebra is nil if every element is nilpotent. It's a particular case of being algebraic. Courage problem, which is an analog of the Burnside problem. If an algebra is finitely generated and algebraic, does it imply that it is finite dimensional? The answer is no. And in fact, Golet and Shafarevich constructed counterexamples to this problem, and then they used those counterexamples to settle the group theoretic problem. Also, there is notion of growth in algebras. Let Vn be the linear span of all products of generators of length up to n. Well, I never said that my algebra has to be associative. So you have to put brackets, but in any case you can do it in finitely many ways. So this is a finite dimensional space. And the union of these finite dimensional spaces is the whole algebra. We can discuss how fast their dimensions grow. And if there is a polynomial growth, if there is a polynomial upper bound, then the degree of this polynomial is captured by this formula and is called the Gelfand-Kirillov dimension of the algebra A. The upper limit. Okay. So the problem is every nil algebra of finite Gelfand-Kirillov dimension of polynomial growth is finite dimensional. So that is a Courage problem, but for algebras of finite Gelfand-Kirillov dimension. Look, the Burnside problem for groups of polynomial growth has positive solution. It follows from Gromov's theorem. So for groups the answer is yes. However, for algebras the answer is no. Lenagan and Agatos Maktonovich constructed examples of such algebras, finite Gelfand-Kirillov dimension, about 30, nil, infinite dimensional, only over countable fields so far. And as far as I could say, the proof is complicated. It's an inductive limit of Golet-Shafarevich algebras. Now I want to talk about another approach, which kind of was outlined in a series of papers of Petrogradsky, Ivan Shestakov, and myself. The approach is following. You know, Lenagan and Smaktanovich, they define these algebras by generators and relators. This is a particular presentation. This is a different approach. So let F be a field of positive characteristic. We consider polynomials over that field in countably many variables and partial derivatives. Then every piece power, for those who keep teaching calculus still remember the formula, every piece power is a constant of these derivatives. Hence, the ideal generated by all piece powers is invariant, and we can factor it out, and our partial derivatives act on this algebra of the so-called truncated polynomials. This is called the algebra of truncated polynomials. Piece power of every variable is 0. And let us consider the following two infinite differential operators. In a way, the idea of these operators came up in an attempt to construct an algebraic analog of Grigorchuk groups. Grigorchuk groups are groups of automorphisms acting on a tree. And these are infinite differential operators. It's clearly related. So, two infinite differential operators. Let L be a Lie algebra generated by these elements. Well, in the it's linear transformations, in the algebra of all linear transformations. And let A be the associative algebra generated by the same elements. So, an enveloping algebra of L. Let lambda be a bigger root of this quadratic equation. Theorem first. This Lie algebra L is nil. So, for an arbitrary element, some big piece power of it as a linear transformation is 0. Second, the Gelfand, it has polynomial growth, and Gelfand-Kirillov dimension is equal to this logarithm. The enveloping algebra A also has polynomial growth. It's just you have to double it. Now I want to formulate a few conjectures. Conjecture 1. This associative algebra is nil. If it is nil, then this is another example of an infinite dimensional nil algebra of finite Gelfand-Kirillov dimension, and we get much better bounds. Also, it works not necessarily over countable fields, however only of prime characteristic. That's true. Another conjecture. Let us consider the universal associative enveloping algebra U. So it's a domain. The fact that it is nil means that given an arbitrary element A of the Lie algebra, in the Lie algebra, that big piece power will be 0 as a linear transformation. It means our U is a domain. It means that the same piece power will lie in the center. That's what it means. But then the center of this algebra U is large. Let us invert all non-zero elements of the center. Consider the ring of fractions. And denote it D. Conjecture. D is an algebraic division algebra. You see, the Courage problem for division algebras is widely altered. The finitely generated algebraic division algebra. Forget about algebra. There is no any example of an infinite dimensional division algebra which is finitely generated as an algebra. That might be one of them. It's like with Grigorchuk groups. After Grigorchuk introduced his groups, they were introduced as counterexamples to very particular problems. But after that, it became clear that they are counterexamples to everything. So we would hope for something like that in algebras. Now, fast growth. In groups I finished with property tau and fast growth. The corresponding notion was formally introduced by Avi Vigderson in theoretical computer science. Let epsilon be a positive number. Epsilon is only a positive number. Have you ever seen epsilon which is not a positive number? V is a finite dimensional vector space over V, over a field F. We consider the algebra of linear transformations and choose M linear transformations. We say that epsilon and this collection T1, Tm is an epsilon dimension expander if the action is irreducible. And second, given any subspace, whose dimension is less than 1/2 of the dimension of V. If you increase that subspace by acting by these linear transformations, the dimension grows at least 1 plus epsilon times. That's a pure analog. And Vigderson asked about a family of epsilon dimension expanders with M and epsilon fixed, but the dimension goes to infinity. M, the number of generators, is the analog of K regularity. You remember K regular graphs, it's K. And again, if there is any way to introduce measure in your field, like a finite field or real numbers, complex numbers, then random matrices would do the job. But again, we are interested in an explicit construction. And of course, the first idea is to find an analog of an algebra with property tau. So that algebra any finite dimensional reducible representations, be finitely generated, and have good expansion property. Then you would take all these representations and the images of the generators would provide you with this T1, T2, and so on. Well, this is the definition. And indeed, in a joint work with Lubotsky, we found such algebras, but only over fields of characteristic P. Our example was sort of non-trivial. Let F sub P be a finite field of order P. We consider polynomials. Then we consider n by n matrices over these polynomials, but which are congruent to 1 mod T. It's like congruent subgroup. If the size is greater or equal than 3, we consider this group, and the group algebra over a field of zero characteristic has property tau. So at least over fields of zero characteristic, we have an explicit construction. Later, it was noticed that we did not have to go that far. If you choose any finite dimensional simple Lie algebra over a field of zero characteristic, then it's universal enveloped in algebra. Already have it. But over finite fields, the question is widely open. And as you can imagine, people in computer science are interested primarily in finite fields. Well, that's the end of the talk. Thank you.
Are there any questions?
The question was, why did Wittgenstein ask about this question? Well, they had a series of papers where they needed dimension expanders. It does not necessarily have that property. Well, we asked that question in our paper with Lubotsky. Now I mentioned the result of Yershov and Hyphen. Let's consider finitely a free ring, associated ring in finitely measured. Then the group algebra. It has all kinds of representation. So it is not true that if you take a group with property P, then its group algebra has property tau. Yes. For tau, yes, of course, yes. Fine. Okay.
If there are no other questions, let's thank Efim for a spectacular talk.